Thank you very much, Zvi, for this kind invitation to present this colloquium. So we have a problem because now we have been working for now to make sure that the presentation would advance and be on Zoom at the same time. So we were there a few minutes ago, but
there we go.
Okay.
Just out of focus.
Okay. Thank you. Yes, so as Vi said, I'm going to tell you about error correction. And what is error correction? Well, when you store quantum information in some physical qubits, there will be always a finite lifetime for this qubit. There's a series of phenomena that go under the name of decoherence, which means that the information is stored only in a finite time. But in quantum error correction, you have a collective phenomenon in which you assemble sufficiently many qubits and you make them interact with each other in a way that out of this collection of qubits, there is one logical qubit that will live longer than either one of the qubits, the physical qubits that participate in this collective degree of freedom. And of course, you want to do this, you want to observe this collective phenomenon, but you want to achieve what we call break-even point, which means that your logical qubit should be better than any of the constituents. And I'm going to tell you how in this experiment that we have done at Yale, in fact, it was a whole series of experiments, as you can see from these papers here, we've been able to go sufficiently beyond the break-even point that we could claim that we had indeed lengthened the coherence time of quantum information. You might say, well, can we have physical qubits that are so bad that in comparison, the logical qubit shines? Well, as you will see, it doesn't help. If you want to really have a very good logical qubit, you have to start already from good physical qubits. Okay, but this is a story I want to explain. And but before I do that, I wanted to present the team that did these experiments. I will present data from two of the graduate students at the time, Alek Akbush and Vlad Sivak, who are now working at Google. And I would like also to acknowledge my colleague at Yale, Rob Sholkov, Steve Gavin, Shruti Puri, and Leonid Glasman. So let's start from the beginning. Before jumping to quantum information, let's just talk about classical information. How is it protected? So classical information is stored always in a kind of switch. Of course, this is a mechanical switch. In your computer, you have more like an electrical switch made of CMOS transistor. And this circuit is such that it has two basic positions here, two basic states. Instead of the position of the switch here, it would be a current through one of the transistor, but you have essentially two deep wells here. And an essential way to implement correction and make sure that your bits in your computer doesn't flip, you have dissipation, so that if the state is perturbed by a little force, a little parasitic noise, it will remain in one of the well. And if you make the well large enough, deep enough, and this is measured by this this energy delta U. If you make this energy delta U greater than the energy of fluctuations, of thermal fluctuations, then this Arrhenius law will tell you that you can have a very, very low error rate, typically 10 minus 16 or 10 minus 18. In fact, in your laptop, the errors are much more likely to come from software error in your operating system than any noise that would flip the bit. So for classical information, friction is absolutely essential, and it is, in the end, this friction that makes your computer use so much power. Your computer basically eats 100 watts of power, and all this power essentially is necessary to maintain, to make sure that the working memory doesn't make any mistake. Now let's go to quantum information. So quantum information is not just 0 and 1, it's also all the superposition of states 0 and 1 of some system. These superpositions, they can be represented by a sphere. 0 and 1 is like a spin 1/2. It's like the spin of an electron. And the spin can point in any direction on this sphere. And now the noise will act in a more complicated way. You can have a random field along Z, a random field along X, and a random field along Y. And you cannot just damp this random field by some friction, because this friction corresponds to basically a lot of degrees of freedom observing your qubit, and this observation collapses the qubit and destroys the quantum information. You cannot really preserve this superposition and damp the qubit at the same time. So you have, so friction, which was our friend classically, now seems to become our enemy. But as you will see, by inventing a clever form of friction, we can actually get correct errors. And that's the purpose of my talk, to tell you what kind of friction, what kind of collective phenomenon can we submit to friction to preserve quantum information. Okay, and this is the outline of the talk. I'm going to tell you about our implementation, which is done in quantum superconducting circuits. I will tell you a bit more about the criterion that we adopt to say that we do indeed error correct. And then I will launch into the code, the encoding that we have used, which was invented almost 25 years ago by this trio of Daniel Gottesman, Alexei Kitaev, and John Preskill. And this is what it is, this encoding that we have implemented. And then I will show you the experimental result and try to convince you that indeed we have made a qubit whose lifetime, whose coherence has been improved. Okay, so superconducting quantum circuits, I think the easiest way is to begin with just an LC oscillator here made of superconducting aluminum. And like any harmonic oscillator, it has a parabolic potential here, and the states are evenly spaced. Now, what is very nice in this quantum system is that you can adjust all its properties, for instance, the energy difference between two levels, by just engineering the inductance here and the capacitance. And yet, at the same time that this is an engineered system, a collective emergent system with billions and billions of atoms, there is one variable either the flux in the inductance or its conjugate variable, the charge on the capacitor plates here. These variables, these collective variables are quantum, and this is their commutator. They are the flux and the charge are like the position and the momentum of a mechanical system. The problem with the harmonic oscillator is that you can adjust its frequency. That's nice. You can make it a few gigahertz so that at low temperatures you could be in the ground state. But if you try to change state, and by shining microwave, the way you shine light on a real atom, in fact, all these transitions are stimulated at the same time, and you cannot go from the ground state to the first excited state. So the dynamics of the harmonic oscillator is a bit dumb. And the problem is this linearity. It's you cannot use a fully linear circuit. You need some kind of nonlinearity. So instead of a parabolic potential, you need a potential that will be something else. In this case, what I have drawn here is a potential that flares up at higher energy, but anything that is not a parabola will do. In that case, the quantized energy levels are not equidistant, and now all the transitions can be resolved. And you can shine frequencies at these transitions and control the system. In fact, the more the transitions are distinct, which is this nonlinearity ratio here, the better. But actually, you need something else. You need that the dissipation, which broadens the level here, is sufficiently small that actually the distance between these transitions is much greater than the width of an individual line. So what you want to actually optimize is the quality factor of this nonlinear oscillator times this nonlinearity ratio. And basically, there's only one electrical component that meets these requirements. It's the superconductor insulator superconductor tunnel junction that was actually proposed by Josephson in 1962. So this electrical circuit is composed of tunneling element here, which for historical reasons is represented by a cross, but you should think about it as a sort of nonlinear oscillator. It's in parallel with the capacitance, because this is a sort of sandwich here. And in what sense is this nonlinear inductance? Well, if I integrate the voltage across that element, I get something which is like a flux. And the energy of this element as a function of this generalized flux starts like a parabola, like an inductance. An inductance would be this dashed curve here, but instead of a parabola, you have a cosine function, exactly what you would have for a pendulum. A pendulum has also a potential energy that varies in an oscillation like this. But unlike a pendulum, this system can be quantum mechanical, and you have energy levels that we at Berkeley a long time ago, now something like 40 years ago, we observed. And these energy levels now, after much improvement, have the quality of the hydrogen level. So this year we have crossed with researchers at Princeton have demonstrated that they could actually make this system with sufficient quality that the transitions are fine enough that they match the fineness of the levels of the hydrogen atom, which corresponds to a Q of about 20 million. Of course, this is far from being an atomic clock atom, but it's great that we are matching now a textbook atom. Okay, so this is what is this artificial atom for some joke reason is nicknamed the transmon, and it is used to implement quantum information in several labs and industries. And in terms of encoding a logical qubit, so I said we need some collective degrees of freedom. We need to assemble several qubits to provide a good logical qubit. Well, there's two ways to do that. You can take individual circuits that behave like two-level systems, and you can make a register out of it. And you will have a Hilbert space whose number of dimensions will grow exponentially with the number little n of qubits. And this is a strategy that is used, for instance, at IBM or at Google. But at Yale, we have followed another pathways, which is the continuous variable pathway, which uses all the levels of an harmonic oscillator to encode information. If you stop to let's say n level, let's say 256 levels, that will be equivalent to 8 qubits, and that's about the type of control we can have on an harmonic oscillator. But the problem is that because the nonlinear, this harmonic oscillator by itself has no nonlinearity, you need to couple this harmonic oscillator to at least one of these synthetic atoms to perform operation. And that's the strategy that we are using here. And there are several codes that use this idea, and I will be talking about this so-called GKP code. But there are also other codes like CAD codes, which are, for instance, pursued at Amazon. Okay. The reason why we chose this way was that this is much more economical in terms of hardware. You need essentially to do error correction, you need essentially one Josephson circuit, whereas here you need one Josephson circuit per physical qubit. So that's more complicated. Okay, now when I say that we have made a logical qubit that lives longer than all the constituent physical qubits, what do I mean? Well, it's here I'm defining the error rate by expanding the fidelity of an operation for small time. For instance, if you do NMR in a nuclei, this would be the rate of error. It's a combination of 1 over T1 and 1 over T5. And so this will be the error rate of each qubit, each of the constituent. And so this gain here is the ratio essentially of the inverse of the rate of the logical qubit error rate to the minimum, to the best qubit in your system. And break even is when this gain is equal to 1. So you want to make this error correction gain as large as possible. And let me tell you now how this code works here. It's a very clever code, and I cannot resist the pleasure to explain in detail how it works. So at first, it starts a bit in a bizarre way. So this code proposes us to encode in an oscillator a wave function that is a picket fence wave function like this. This is probably something you have not seen in any quantum mechanics course, but it's perfectly allowable. Basically, you have peaks in the wave function, and these peaks are regularly spaced. And this is going to be your zero, your logical zero. Now, the logical one is going to be the same picket fence wave function, but translated by half a period. Now you intuitively understand why I can error correct in some degree with this wave function. Imagine that there is a force that randomly shifts the wave function. So you see if the shift is less than half the distance between the green and the purple peak, you can still recover the information. It has not been scrambled. So if you can detect this overall translation before it scrambles the true state, you will be able to protect the information. That's in a nutshell the principle of the code. It was invented for these translations and didn't seem to be very physical because actually the noise in these quantum oscillators is not too much a translation noise. It's much more the loss of a photon. But it was actually realized later that this code was also optimum if the energy of the oscillator would be lost for one photon at a time. So let me introduce, in order to understand this code in a more deeper way, I have to tell you how we represent the quantum state of an oscillator. We are represented by a sort of phase-space portrait. So Q is the position coordinate and P is the momentum. A classical state would be a point, only a point in that two-dimensional phase space. But quantum mechanically, you have for the ground state, instead of a point at the middle, you have a first disk because of quantum fluctuation. If you excite the oscillator and go to the Fock state number 1, which corresponds to 1 photon, then you have this interference. You, instead of a red, a positive value at the center, you have a negative value, and then you have a line of node here in white. When you increase the number of photons, you have more line of nodes, and the number of lines of node correspond to the number of excitations. Now, you can do other states. You can make other states. For instance, you can displace the vacuum. That's called a coherent state. Here, I have displaced it by 2 units here. You can squeeze, you can shrink this disk in 1 dimension. Of course, it will extend in the perpendicular dimension because you have to conserve area. And if you would, for instance, superpose 2 coherent states on opposite side of 0, you would get the cat state here. And you see an interference pattern in between these 2 blobs here, which show that the 2 blobs evolve coherently. Actually, you can use these cat states also to protect information, but I won't go further here. What I am going to tell you is about this GKP code, which actually uses this squeezing. You've seen these picket fences, and they correspond to a superposition of a squeeze vacuum. And when you superpose this squeeze vacuum, actually you get in phase space an interesting interference pattern. You get both lines like this, but you get columns also like this. The column, you understand, they come from the fact that we have this picket fence. In fact, if I sum along these red dots here, I will get a spike in position. But you see that if I sum these dots horizontally, I will, in momentum, get spikes also. And this comes from the fact that the Fourier transform of a Dirac comb is also a Dirac comb. Now, if you look closely, you will see that these states 0 logical and 1 logical are actually just shifted with respect to each other. So you have this interference pattern both for 0 and for 1. What to understand why actually a simple translation is going to do a qubit operation, I have to tell you something absolutely amazing, a very simple way to understand quantum mechanics that's different from every other way. And this is actually explained in this charming little book here. This is an invention that was made during World War II by two theoreticians, Grunwald and Moyal, but it's not very well known. John Preskill and Daniel Gottesman exploited this, a marvelous idea. So what is it? So if you do a closed circuit in phase space, classically, nothing happens. When you come back here, the system is just what it was. But quantum mechanically, the system acquires a phase factor, which is just given by the area of your loop divided by h bar. And this is what they are exploiting in this code. You can, instead of translation here, you can talk about displacement operators with complex arguments, but that's not important. What is important is that you can choose certain displacement, which are well with the right length here, and those displacements can enclose an area which is going to be a two-action quantum, 2 times the Planck constant. If you do that, what you discover is that this displacement commutes because the phase essentially acquired here, the phase factor will be exactly unity. And you can take this displacement as the identity in the code. So you can say, well, if I displace by this I here, I should get the same wave function. And that corresponds to this period of this picket fence. Now, I'm going to do a very simple Euclidean geometry. So the area here is 4 pi h bar in total. But now let's look at the area of this triangle, little triangle here. So this is a triangle which has x on this side, z on this side, and y on this side. Those are these 3 translations of that borders the triangle. But if you look at this area, it's exactly 1/8 of the total area. And that gives you a pi over 2 phase shift, which means that the product of x, y, z is exactly equal to the complex number I. But that's exactly the algebra of a spin 1/2. It means that x, y, z correspond to essentially the 3 polymatrices of a spin 1/2. It's hard to believe because actually I have done translations in a flat space, but these are exactly like the 3 pi rotations in space. They behave exactly like this. So this should convince you that we have the operations to act on a qubit. Now, there's another thing I have to tell you. So we cannot really do a true picket fence that would have an infinite number of peaks, because that would cost you an infinite energy. We have to have a finite envelope. So the envelope is shown here. And by conjugation, you would discover that if you impose a finite envelope, your peaks now cannot be perfectly sharp. And so when we look at the phase space of our qubit, we see dots here that fades out as we go to a larger Q or P, or essentially larger energies. But this is still perfectly fine for encoding, and we can use this finite energy code to encode the logical qubit. So what what does error correction mean in that space? Well, it means to impose a certain amount of forces that are pictured by the blue arrows and the purple arrows. So the blue arrows, they sharpen the peak. It's a dissipation that tends to sharpen the peak. But due to the Heisenberg uncertainty principle, we have to act on the outside here by the purple force that contains the envelope. Because if we sharpen the peak in one direction, let's say in P, then the wave function would expand in the Q direction. So we have to maintain these shapes here. And this is what the error correction consists of, implementing this dissipation and forces. Now, how is this done practically? Well, it's done with a superconducting system that is composed of a microwave cavity. So this is a cylinder, a hollow cylinder. There's a post at the bottom here. And this has essentially one microwave mode, its frequency is about 4.5 gigahertz. This by itself cannot be controlled, but to control the state, the quantum state of this cavity, we have this artificial atom, our transmon auxiliary atom, which will manipulate the state. But this is not sufficient. We need to evacuate the entropy. Basically, error correction is chasing entropy in your system, and at some point you have to get rid of it. And this is done through this exit readout resonator. And basically, the entropy goes through this port here. And so these are the frequencies of these various degrees of freedom. I have to thank Suhas Ganjam here, who has helped us get one of the best possible transmon at the time. Okay, now how do we remove this entropy? How do we use this artificial atom to this ancilla qubit here to remove entropy in the system? And this is done by one operation, which I've labeled the Swiss Army knife of this experiment, because it does absolutely everything. It's called a conditional displacement gate, and it is performed by sending a series of pulses both to the ancilla qubit and to the cavity. And the pulses are a bit like echo pulses in nuclear magnetic resonance. But the function of this gate is the following. Once you perform this sequence, in fact, you've displaced the cavity by an amount. So I started here with the squeeze state at the origin, but it was displaced up if the qubit was in E, and it was displaced down if the qubit was in G. This is why we call it conditional displacement. And this operation, which is an operation that mixes the degree of freedom of the cavity and the atom, is all you need to do error correction, and in fact to prepare any state in the cavity and actually read it out later. Okay, so just to, I don't want to go in the detail, but by sending those pulses to the cavity and the qubit, we can prepare any state. And here I am just giving you the sequence we use to prepare a particular GKP state. You see that this whole sequence lasts a few microseconds, and after this time, we are preparing a state. So these are experimental results, and we can prepare different states of our logical qubit. So for instance, plus Z is a state that points up. If you imagine this abstract sphere, it would be like a spin pointing up, and this is the Wigner function of that state. It could point in the plus y direction or the minus x direction. You see, we can actually prepare any state that we want in this cavity. And this shows that on average for these states, we have about 5 photons worth of energy. So the state is a complicated state. It's a superposition of many Fock states, but the average Fock state number is about 5. Okay, now with this gate, we can prepare any state, any initial state that we want, but we can detect also when an error happens. So let's say, suppose you have prepared this finite width picket fence wave function, and then suppose an error happens, it is translated by a small amount epsilon here to the right. Well, you can use this conditional displacement gate and combine with proper rotations of the auxiliary qubit, you can detect 1 bit of information on this displacement. This displacement epsilon, by this operation, is mapped into a rotation of the qubit in the equatorial plane. So if you have prepared the qubit along x, the qubit block vector will have rotated by an amount exactly proportional to this displacement. You see, we have a mapping of displacement in phase space with rotations of spin. And so now, if you measure, let's say, if you measure along y, the direction along y, you will learn whether your epsilon here was positive or negative. You get 1 bit of information. If you repeat the sequence enough, you will learn exactly the errors, and you can correct them. To test that this works, we have to calibrate this operation. We have to, and this is done by preparing the qubit both in state of superposition of the ground and the excited state, and that produces 2 types of rotations in phase space for the cavity, and then there's an interference pattern, which we can measure here, and from the period of that interference pattern, we can calibrate the gate very precisely. Now comes the best part, in my opinion. So at first, we were doing these experiments by detecting the displacement and correcting it actively. So we were sending the information outside our refrigerator and back. But then there was this discovery by Steve Gervin and Baptiste Royer and Chandra Singh of an algorithm that was doing the correction autonomously. So we didn't have to measure and correct. We could do a series of operations would shift automatically the entropy from the cavity to the dump of the qubit, this readout port. It's quite complicated to explain in this talk why this particular algorithm does this, but you can think about it as a form of cooling. You are able to remove the entropy that is created by this random displacement, and basically this amounts to a sort of artificial friction that takes this grid and repositions it correctly in space, in phase space, without observing the pattern of state. So this is completely, it doesn't, this method doesn't really look at the color of these dots. Whatever the color, which would encode which state you have, it really recenters the grid. So this is the error correction that is done. Another way to look at this error correction is the following. So you have encoded in the state of the cavity a spin, a qubit, in a complex superposition of Fock state. But there are essentially two errors that can happen. You can either lose a photon, so this is this operator A, the annihilation operator that loses a photon, or you can gain a photon. The cavity is at low temperature, but it interacts with an atom which you manipulate. So you put energy in the system. So you can either lose a photon or absorb a photon. Each time this process happens, you go to a different spin, you go to an error, and you shouldn't have this happen too many times, because at some point there's an horizon here, and you will fall over a cliff, and then you are doing an uncorrectable error. But if you are not over this cliff or over this barrier, what you need to do to return to this ground manifold is to have this friction that each time you go up this ladder will bring you down. And this is what our error correction does. So this is why I was talking about a form of cooling. It's in contrast to the standard form of cooling in atomic physics, which bring you to a ground state. This cooling actually brings you to a manifold. So it's two states at a time that you cool without ever looking at which one of the two states is actually populated or even superposed. So this is what basically what quantum error correction is cooling the system, but two states at a time and never looking at which superposition you have in these two states. Okay, so does it work? So this is an experiment where we see error correction in action. So we start by preparing states in the cavity. So actually we are preparing, in this kind of example, plus z and minus z. This corresponds to this logical spin or logical qubit being either up or down. Of course, this is abstract because in the cavity there's no such thing as up and down. And then we apply error correction, and this actually cleans up our initial state, which was not optimum. And in the few hundred cycles, the state is stabilized. We have logged the state to the grid. And then, as you see, as we error correct, eventually we lose our information because our error correction is not perfect. This qubit is not going to live forever. After about 2 milliseconds, remember, we are correcting every few microseconds. So this is a large number of cycles. Now, at this point, you see, you cannot really distinguish the two states. There's no blue anymore, no negativity in the Wigner function. And so this is a random superposition of the two initial states. But how have we done? How good is this error correction? So we have to compare our logical qubit, which essentially lives about 2 milliseconds here. Let me remind you that an error correction cycle is 5 microseconds. So this logical qubit lives about 2 milliseconds if you average. There are different times corresponding to the direction x or z or y, but on average it's about 2 milliseconds. Now we have to compare these 2 milliseconds to the best qubits in the system. So first of all, our transmon, our auxiliary atom doesn't live very long. It's about, on average, it's about 250 microseconds. So that's this pillar here. The next best state is if you would encode information in the superposition of 0 and 1 photon in the cavity. That's this pillar here. This leaves about 800 microseconds. So you see we have a factor here. We beat the best qubit in the system by a factor 2.3. So this is what we mean by actually prolonging the coherence of the system by a collective effect. Okay. That's I'm arriving at the end here. So we have indeed in this experiment for the first time corrected all errors. So we have really prolonged the coherence of the system through this collective effect. Something that I didn't want to, I thought I wouldn't have the time to discuss is that in this experiment there's a lot of important calibrations that need to take place. And the calibration is done by actually reinforcement learning. So in fact, it is the computer that calibrates the system and finds the skewness that we haven't discovered ourselves. So what has been very useful in this experiment is that these machine learning techniques, which I thought would be at first, when we started to apply these techniques, it was not very convincing. And I had the impression we were just following fashion here. But in fact, it turns out that for error correction, learning the exact parameter of your system was absolutely crucial. So compared with the manual optimization of the experiment, we're gaining about a factor of 2. So since we, in this experiment, we lengthened the coherence by a factor of 2, you see that this reinforcement learning technique was essential. By the way, what we have done is model-free optimization. So we let the computer, we let the neural network discover some skewness that we had not planned in the experiment. This is quite important. Now, I need to say, of course, express a caveat here. So what have we done? We have taken a memory. We have a qubit that was actually memorized, and then we've been able to lengthen that memory time. But of course, quantum information is not just memory, it's also a gate operation. And the frontier now in quantum information is to correct the errors of the gate themselves. And so this is where the field is at the moment. It has not been done, but it is expected to happen in a few years as the field progresses. So for our particular implementation, we would want to do a C0, for instance, and protect a C0. And but a C0, when the qubits are encoded in cavities, are not too complicated. This is a transformation of the two-phase space with this simple linear transformation, and that's a big advantage of this GKP phase space error correction. And this is actually pursued by a certain number of labs at the moment. Now, I also don't want to leave you with the impression that storing information in cavities is the end method. in error correction, you have different levels where each level corrects errors of the level below it. And so these so-called bosonic codes in which you encode information in a cavity can be one particularly hardware efficient for the first layer, but the next layer can be other type of codes, and in particular, you can use codes like the surface code that do quite well when it comes to fault-tolerant operations and fault-tolerant algorithm. Okay, so thank you for your attention.
Great talk. We have questions.
I have a couple of questions, if that's okay. So my first question is, I see that like you define like the like the envelope for your GPU code. What like line shape is that envelope? Is it a Gaussian?
Yes. Thank you for asking this question. Yes. So indeed, we choose. It's not absolutely necessary, but in our experiment, this envelope is Gaussian, and the peaks are also broadened in a Gaussian way.
I guess for another question, I see that you define like QAC cycles. And are you doing the error correction autonomously for this experiment, or?
Yes. So yes. Let's see. Yes, there are different. So you can do the you can actually do the error correction non-autonomously. You can measure actually this bit of information and then act from the outside and do a counter displacement. But you can actually in this very clever algorithm, what happens is that you encode, you see you have displacement delta, which could be any small displacement in the plane. And this displacement can be mapped to the X and Y component of the qubit simultaneously. And then basically, once the qubit has, this auxiliary qubit has been displaced in this way, it basically you have transformed a displacement in 2D into a little rotation in 3D. You reset the qubit. So you throw away this information, and that produces a back action. You know, in quantum mechanics, measurement is invasive. It perturbs the system. But in that case, the perturbation of the system, on average, has the effect of locking this grid to a particular grid fixed in advance. So it implements these blue forces that I discussed. So if you want this autonomous error correction, when you look at it, what it does, this you know, this reset of the qubit, if you think about it, it's a sort of dissipation. You don't read the information of the qubit, you reset it, but that essentially removes the entropy of the qubit. And that has the effect of creating these pseudo forces, pseudo dissipative forces that are represented by these blue and purple arrows. So it forces, if you want, what it does, it forces the manifold of state to have this Wigner function. And this Wigner function actually contains two states. So it's a way to bring the state of the cavity to a manifold. And you can, of course, my explanation is not detailed enough, but you can convince yourself that establishing this array of forces can be done without actually knowing the underlying information. So you see, basically, you see the grid of dots is the same in the 0 and 1 logical. It's just that the pattern, the blue, the negativity, the Wigner negativity is shifted by 1 unit. But that's not, the force is not knowing this at all. It is completely agnostic. So we have established a force that brings this grid in place, but is completely agnostic to this translation here by half a period.
Thanks for the nice talk. For the microwave resonator implementation of this, I have a question about the transpons there. I think you said a few times there's like a trapped ion and trapped atom or something there. Is that actual like physical trapped ion, or is it one of those?
Yes. So thank you for this question, because indeed I didn't have time to say this, but okay. There is actually a competing line of experiments done, for instance, in the group of Jonathan Home at ETH, which uses trapped ions. And the trapped ion implementation works at the level, the upper level of the Hamiltonian. It's very similar, but in practice, it's completely different. So what we use as an harmonic oscillator is a microwave mode, a standing wave in a superconducting cavity. What they use is actually a phonon mode of a series of trapped ions. And so in their case, the information is stored in a mechanical mode. It's really a phonon mode of these ions. The problem is that the trapped ions themselves are extremely good qubits, but this trapped ion mode, these vibration modes of the ion, doesn't have a very good quality factor. And so we have the advantage of having a very good mode. Actually, in the situation is completely reversed. So their ancilla qubits are extremely good, but their oscillator sucks in some way. Our situation is completely opposite. We have an excellent oscillator, but our atom is not that good. In fact, most of the errors we correct are errors that are coming from the atom itself and that propagates to the cavity. In fact, out of 10 errors that we correct, 9 have actually been produced by the transmon itself.
Quick elementary question. So you have decoherence in the bosonic system and decoherence of the ancilla qubit. For break even, like it gets better than both?
Oh, yes, yes. So yes, absolutely. So, but yes, so this is the sort of budget that I'm describing here. So this is the logical qubit. And these are the two best qubits, both for the artificial atom and the cavity. The cavity, as you see, is much better than the atom. The atom lives on average 250 microseconds, the cavity 800. But when we combine both, when we combine all these degrees of freedom, so we end up with about 8 effective degrees of freedom, because we use more than 2 levels for the cavity. We use about typically 100 of levels. So this collective Hilbert space houses one qubit. There's a combination of wave function in that big Hilbert space, which lives longer than any of constituent degrees of freedom.
Which number is the lifetime of the boson itself?
So no.
Cavity.
So look, for instance, this lifetime is actually the lifetime of a single photon in the cavity.
That's what's the number? Which one is it?
So it's about, if you look at this curve, it's,
600.
yes, it's 600. That's the lifetime of a photon. Yet the encoded information in this very clever GKP states can live with error correction, can live 2 milliseconds.
Okay.
So that's basically this improvement is this arrow, this GKP bar here correspond to this collective degree of freedom.
Any other questions? One more. And what was it? What set this 4.7 bin bar? This sort of your finite support?
Yes. Thank you. That's also thank you for this very nice question. So yes. So let's go back to this slide. So yes, what sets this? Well, it's a compromise. So of course, the larger the number of photons, the bigger the superposition, and the sharper is going to be the dots. You're going to have a bigger envelope, and the dots can be much sharper. But because the envelope is bigger, the time that photon take to leave is actually shortened, because an excited state, a Fock state, has a lifetime that goes like 1 over its quantum number. So by mixing in photons with too high quantum number, we speed up the relaxation. So this 4.7 is exactly the compromise.
Is it like the effective curve distance supposed to outrun that? Isn't that the point?
So suppose let me so if we will increase the number of photons, the distinguishability of the peaks would become better, but then the decoherence would be faster, and we would have to run the algorithm faster. We would have to shorten the error correction cycle, but there are certain limitations, and basically the limitation is how fast we can do operations on the transmons. And so if you want, this number is a sort of compromise between the speed with which we can error correct, the speed at which we can ship entropy away, and the speed at which entropy sets in.
Okay, well, thank you.